Okay, so let us say some words about Steiner grids. So pretty much what I'm going to do is now knowing that every Möbius transformation is conjugate to a standard example, what I'm going to do is to use the conjugating transformation to pull the families of curves that we found for the standard examples to the general situations. So it's really going to be rather straightforward, but okay. But let's do it carefully. And so what's going to make the analysis work is that Möbius transformations are always holomorphic from C bar to C bar, and their derivative is never zero. And which is what I say here, which implies that they are conformal at every point, right? So they always take angle of intersection to angle of intersection, right? So that is, if I have two curves in C bar and they intersect at a certain angle, and I take their images on their Möbius transformation, then at the intersection point, which is the image of the intersection point, when I measure the angle, it gives me the same angle as originally, right? So that's what I have. In particular, when if I have two orthogonal curves, their images are orthogonal, right? So now for the derivative, one only has to be a bit careful that we're seeing C bar as a Riemann surface, right? So when we have a Möbius transformation that is from C bar to C bar, we have to be careful when we work around infinity, because we have to consider the charts around infinity, both in the domain and in the codomain. But otherwise, for the finite points that do not go to infinity under the Riemann under the Möbius transformation, one computes the derivative just as in the basic complex analysis, and one sees that their derivative is this number if the Möbius transformation is given by the matrix A. So this is not zero. And then here there is the exercise that in the point at infinity, both in the domain and in the codomain, you have to compute the derivative, and now of course using, as I said, the charts around infinity, and verify that it's not zero. So as I said earlier, the takeaway from this is that then Möbius transformations are conformal at every point, and hence they preserve angles of intersections between curves. Okay, now another exercise. Suppose that I have a parabolic Möbius transformation. Okay, as we have seen, if it's parabolic, that is by definition that it has exactly one fixed point, then it is conjugate in mod plus of C bar to a translation, and hence to any translation, because we've seen that all translations are conjugate in mod plus of C bar. Okay, so take two Möbius transformations that conjugate two translations, right? So here I have two translations to which nu is conjugate. Say that they are translations, say by the vector by the non-zero complex number beta and the non-zero complex number beta prime. Okay, so they are translations, right? So let's say tau nu tau inverse is a translation, and sigma nu sigma inverse is another translation, right? So the directions, which are beta and beta prime, they may be different. But so the exercise, what it asks is that when you consider this composition, it takes the direction beta. It takes the direction beta to the direction beta prime. And so here, let me just correct this, because here it should be beta prime. Oops. Yeah. Okay, so that this composition somehow like a going back to the new plane and then going to the new sigma inverse plane. The direction of beta goes to the direction of beta prime, and similarly, the direction orthogonal to beta is mapped to the direction orthogonal to beta prime. Right. So here you can see the picture here. Here I have I have the fixed point of my parabolic transformation, and then when I apply tau, this point is sent to infinity, and then tau inverse is translation by this vector beta. Similarly, when I apply sigma, sigma of this point is also infinity, and sigma inverse is translation by this beta prime. And then what I want you to show is that whenever I take a line parallel to beta, sigma tau inverse sends it to a line parallel to beta prime. Why am I doing this? I'm doing this because then this means that it doesn't matter whether I choose to use tau of sigma. I get the following well-defined family of curves on passing through the fixed point. Namely, let's say take tau and take tau inverse, and then take all the lines parallel to beta, and map them through tau inverse here. So of course you get, since all of these lines pass through infinity, what you get here is a bunch of circles in C bar passing through the fixed point of nu. So they all pass through that, and then since these ones share only the point at infinity, all these circles in C bar are actually tangent. Okay, and the thing is, since I'm saying, okay, do this for tau and for beta, which is the translation vector of tau inverse, and then you can say, okay, but how about if I want to use sigma and beta prime, which is the translation vector of sigma inverse? And the exercise, the fact that the parallels here go to the parallels here, the parallels to beta go to the parallels to beta prime, tells you that it doesn't matter if you choose to map this here, or you choose to map this here using a sigma inverse, you get the same family of curves. Okay, and similarly, we map all the orthogonal ones, which you see they also share only the point at infinity here. So when I map them through tau inverse, they are all tangent in the fixed point of nu. And because of conformality of tau inverse, this other family of curves is orthogonal to this one. Okay, so these two families of curves. So I have one family of curves, all of them tangent to each other in the fixed point of nu, and I have this other family of curves orthogonal to the original one, and again all tangent to each other at the fixed point of nu. Um, uh, I called that pair of families the Steiner grid of nu. Okay, so this is this definition. Okay, so here you are, right? So it's tau in this S of nu is tau inverse of these guys, and this P of nu is tau inverse of these guys. Okay, so I have these two families of curves. So you see, I pretty much what I did was take the straight lines that are stable on their translation by beta, and I map them through the conjugating Möbius transformation. I pulled them through the conjugating transformation, and then I took the orthogonal family, which is permuted by the translation by beta, translation by beta, and then I also mapped it. So what do I obtain? I obtain an orthogonal. I mean, these two families are of course orthogonal here. They all share this point, and what happens since S of nu is obtained by pulling the curves that are stable on their translation by beta. It turns out that each member of S nu is stable under nu. And since nu permutes the family, this family, the orthogonal family, it turns out that the other family, this P nu, is permuted by nu, and this is rather straightforward. It's just an exercise in conjugation, and somehow what is fascinating is the geometry, right? So here in orange, I'm writing the curves in S nu. So S nu is in orange, and P nu is in red. And let's say so we know that these are all circles in C bar, and we know that circles go to circles on their Möbius transformations. So a red circle always goes to a red circle, right? And somehow what happens is that, for instance, let's say consider this curve that hopefully you are seeing how, right? So consider that one. So let me do it maybe with this. So consider this one, right? So that one, since I'm saying that S nu, I'm drawing it in orange, that one is stable under the action of nu. So what happens is that, let's say that this point goes to another point, another orange point, and let's say, for instance, that it goes to this one. Then the behavior is that then in this other one, this one goes to this 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 one. So you see, it's kind of so you can see that the fact that here this tau nu tau inverse is given by translation by beta somehow is still, you know, reflected here. So this is how more or less the translation looks like. And then let's say if we do it once more, then it may be that well, here I didn't quite draw correctly, but because it has to be kind of here slightly shorter, and then that would be the next step. And then let's say that the preimage of each of these points on their nu, then it would be something like this. All of them lying on R red circle, right? So um, so 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 this is more or less how the translation by beta would be kind of mapped to here. Uh, so 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 somehow you see translation by beta, while here it kind of it just, you can see it goes only in one direction. Here that direction sort of looks like coming from the fixed point and going back again there, right? So something like once and then again and then again. Of course, the order is infinite, right? You don't reach infinitely many steps. So that's more or less. So for instance, this when you start applying, um, somehow this one goes first here, and then goes to another, 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 and then etc. And then it ends up somehow like converging again to the fixed point. Okay, so this behavior is kind of it's perhaps more uniformly sketched or drawn on the actual sphere S2, right? So here again, I'm here. This one is the fixed point, and then each of these orange curves is stable. So let's say that somehow the flow of nu is, let's say, like here. Then maybe let me in small steps. Then it is somehow consistent here, right? So this would be more or less how the iterations of nu can be kind of sketched, or how a mental image can be formed, right? So with this sketch, somehow this red circle, which is kind of orthogonal to the stable ones, goes to another one, let's say this one, right? Along the orange lines, right? Sorry, sorry, the other way around. This one goes to this, will be going to this one, along the orange lines, right? I mean, because of the way I chose this flow instead of going that way. Okay, so that's more or less the behavior we can imagine for the parabolic transformations. Okay, and now let's move on to the Steiner grids of the other Möbius transformations. So far we have defined what is the Steiner grid of a parabolic transformation, and then which is a pair of mutually orthogonal families of curves, and we've made a basic analysis of how of the behavior of nu, of the geometry of nu using these two families. And what I pretty much did was just to map what I already knew for translation, just map it to an arbitrary parabolic transformation. So okay, so now let's go to the other transformations, which are the ones that that have exactly two fixed points. So first I define everything in terms of just a pair of points, and then I go to the transformations. So let's take two distinct points of C bar, of the extended complex plane. And then I call an Apollonius circle an Apollonius circle of the pair, of the unordered pair, to be any subset of C bar of the following form. Now, I distinguish two cases. One case is the first case is that is if infinity is one of these 2 points, and the other case is when both points are finite. So if infinity is one of the 2 points, let's say that it's Z1, and then an Apollonius circle is simply any circle in C centered at the finite point. So if one of the points is infinity, then the Apollonius circles of the pair are simply the circles in C centered at the finite point. Okay. And in the case where both are finite, we take the Apollonius circle of the pair for the real number, the positive real number R, to be this topological closure of the set of all z's whose ratio of distances, of norms, of Euclidean distances to the points is constant and is given by that real number, right? So the ratio of these two distances is constant. By the way, this is the closure is needed only when R is equal to 1, because when R is equal to 1, you actually this set is actually the mediatrix, so it's actually a straight line. What I want to add then the point at infinity, so that this is why I close. But otherwise, when R is not equal to 1, you don't need this one. The set is already closed. This set is already closed. Okay, so those are the Apollonius circles of the pair of points. Here we can see some of the Apollonius circles of 0 and infinity. So as you can see, they are simply circles in C centered at 0, which is the finite point among 0 and infinity. Let us see some of the Apollonius circles, let's say now of 0 and let's say 50 plus 40 times I, which in Python is j. Okay, so that is how some of the Apollonius circles of these 2 points look like. So notice that here actually 0 is around here, and the other point, 50 plus 40j is around here. So it looks like, again, these circles are somehow centered at 0 and at the other point, just like in the previous case. In this case, one can think, in the case around infinity, one can think that these circles are centered not only at 0 but also at infinity. And the theorem is that well, first that if you take any Möbius transformation, you have your two distinct points, and then you take any Möbius transformation that sends 0 to one of them and infinity to the other. And the theorem is that Apollonius circles of 0 infinity are mapped to Apollonius circles of Z0 and Z1, and conversely, the inverse maps Apollonius circles of your given pair to Apollonius circles of 0 and infinity, right? That, in other words, while here I have an intrinsic definition in terms of only Z0 and Z1, I could have taken the definition of Apollonius circles to be just the image of this of the Apollonius circles of 0 and infinity under any Möbius transformation, right? I mean, mapping 0 and infinity to these guys. But it's always nice to have, a direct definition that doesn't require to take them, to map them through a Möbius transformation. Right? Okay, so that's the theorem, and well, we prove it. I prove it in a case where both Z0 and Z1 are finite, and I will leave it as an exercise at the end to show to see what happens when one of them is infinite. But so my proof in this case, in the case where both of them are finite, is based on the following. So I have my two finite points, my two complex numbers, and then the exercise is that every Möbius transformation sending Z0 to 0 and Z1 to infinity is necessarily of this form, right? So for some lambda, so that anyone that takes Z0 to 0 and Z1 to infinity can be written in this form. Okay, so using that exercise, so here it should be 21. Well, since I started with a Möbius transformation sending 0 to Z0 and infinity to Z1, its inverse, since it sends Z0 to 0 and Z1 to infinity, right, must fall in this category. So it should be possible to write the inverse in this desired form. And for instance, this desired form, it automatically tells you that mu inverse maps infinity to lambda. In other words, that mu a of lambda is infinity. And here you see here you have how to determine this lambda in the exercise, because it's the preimage of infinity. And now we compute. Now look, mu a of lambda is infinity. So this means that when I consider the Apollonius circle here, the Apollonius circle, in 0 infinity, where R is the norm of lambda, that Apollonius circle of 0 infinity, where I have here lambda, and of course here it's 0. That one has a point that is mapped to infinity. So that's the circle that is mapped to the mediatrix of Z0 and Z1. But other than that, I mean, for all the other Apollonius circles of 0 infinity, the ones where the R here is not the norm of lambda, I know that that entire circle for R different from the norm of lambda is mapped to a finite circle by mu a. So this means that for them I don't have to pay special. I don't need to be especially careful. I have to be especially careful only for R equal to the norm of lambda. Okay, and then I start the analysis. So for a given R, the Apollonius circle of 0 infinity with respect to for that positive real number R is by definition this one, right? Here you can see it because that 0 is 0. Well, here, and well, for those, of course, for any Z, I know this, right? So from here to here, I have not changed anything. Now, okay, and now when R is different from the absolute value of lambda, here of course, I can take MA of Z and then just say okay, and then to this you have to apply MA inverse, right? But MA inverse is is dictated by this, right? So this is how you pass from here from here to here. When R is not the absolute value of lambda, when it is the absolute value of lambda, then you can just use this convention that we had said earlier before. Okay, and then you see then kind of you just change variable, right? Because you just call this W, right? And then you pass this dividing. Okay, and then here I take the closure again, just because here so that these are, I take just complex numbers. Okay, and then this is closure, but then this is a homeomorphism, so I can put the closure inside. But when I put the closure inside, what I get here is precisely, you see, compared with this, is precisely this Apollonius circle of Z0 and Z1. Okay, so this means that this Apollonius circle of 0 infinity is mu A inverse of this Apollonius circle. Okay, so this means that mu A takes this Apollonius circle in one-to-one correspondence to this Apollonius circle, and mu A inverse conversely. So this proves the theorem in this case, right, when both of them are finite. And the exercise I leave to you is to prove the theorem in the remaining case. Okay, as a corollary, you see, from the very beginning I called Apollonius circles. It's obvious that these are circles in C bar. But how about these ones? Right? I mean, are they circles? I'm calling them circles, so they better be, right? And so since Möbius transformations take circles to circles, the theorem in particular proves that the Apollonius circles of any pair of distinct points are indeed circles in C bar. Okay. Right. And next, you see now also, of course, we would like not only that whenever you map 0 and infinity to your two distinct points, Apollonius circles of 0 and infinity go to the other ones, right? But rather than that, for every Möbius transformation, if you take 2 points you take 2 points and their images, then the Apollonius circles of these ones are mapped to the Apollonius circles of the other ones, and that is the case, right? And the proof is just, if you have your Möbius transformation, then and you have your two distinct points, which of course then are sent to these other points. Then just factorize this nu as a transformation that first sends these 2 points to 0 and infinity, and then 0 and infinity to these guys. And this can be done very easily, so I leave it as an exercise. So under any Möbius transformation, if you fix 2 points, the Apollonius circles of these 2 points are mapped to the Apollonius circles of the images of the two chosen points. Okay, so Apollonius circles are really well behaved on their Möbius transformations. That's what this says. Okay, so now we have one family of circles associated to a pair of points, right? Just like for 0 and infinity. I mean, for 0 and infinity, we took the family of circles in C centered at the origin, and then what we just did was to map this family of circles into what we are calling the Apollonius circles of an arbitrary pair of points. Okay, now how about the other circles determined by 0 and infinity, namely the circles that join them, right? And which are since they pass through infinity, each of them is a straight line union, is of the form straight line union infinity, where the straight line passes through the origin, right? Okay, so let's take that family, which already popped up when we were analyzing translations. Homotheties and rotations. Okay, and then let's map through Möbius transformation. Well, the Möbius transformations send circles to circles if they pass through 0 and infinity. Now, and they all share 0 and infinity, and then I map them. They are circles in C bar that pass through my two given points, right? So this is the other family, right? So if I have two distinct points, a common circle of the pair is any circle in C bar passing through both of them. And what I just said, all the preparation for this definition was simply the fact that this definition is given so that these circles can be obtained by taking any Möbius transformation that sends 0 to this one and infinity to this one, and then map the circles passing through 0 and infinity through that Möbius transformation. Okay, so again, since Möbius transformations are holomorphic with nowhere-vanishing derivative, they are conformal everywhere. Hence, the family of Apollonius circles at the pair of points is orthogonal to the family of common circles. Right? So this is why, simply because in the case of the origin and infinity, the Apollonius circles are obviously orthogonal to the common circles, right? Because simply the common circles are straight lines that pass through the center of any of the Apollonius circles, right? So they are obviously orthogonal. So when you map them through a Möbius transformation, with a Möbius transformation, you really obtain the orthogonality is preserved. And these two families foliate C bar minus the 2 points, right? And by this, what I mean is that for each of these two families, once you delete Z0 and Z1, once you delete the 2 points, C bar minus those 2 points can be expressed as the disjoint union of the curves in the family, right? So for each of these two families, you have this phenomenon that C bar minus Z0 and Z1 is the disjoint union of the family, right? So in the case of the common circles, you know, if you have your 2 points, the foliation somehow looks, well, this is not very, I'm not very good at drawing, but etc. Let's say one more. Whereas the Apollonius circles, the other foliation looks like this. So you have two families, each of which foliates C bar minus the 2 points, and they are orthogonal. The two families are orthogonal in the sense that any curve in one family is orthogonal to any curve in the other family. Okay, and these two families, the pair of families, is going to be called, I'm going to refer to it as the Steiner grid of the 2 points. The sum of the common circles in C bar of 0 and infinity. So since they are circles containing infinity, they are, of course, they must be of the form straight line in C union infinity, right? And then passing through 0, well, those straight lines have to be lines through the origin. So it is fairly obvious that this must be the picture. So let's see some common circles between, say, 0 and 50 plus 40j. So the picture is rather straightforward. So this is how they look like, and they go through both, right? examples of the Steiner grid. So this is this is how the Steiner grid of 0 and infinity looks like. So you can see both families, right? The family of common circles and the family of Apollonius circles, which are in this case very simply defined, just the circles centered at 0. Which you can think also as circle centered at infinity, right? As I've said several times. And now let's change and see the other between 0 and 50 plus 40j. Right? And the Steiner grid looks like this, right? So there you can see the common circles and the Apollonius circles. Right, and here, I mean, you can at least see here how they are really orthogonal, both families. Okay, and the theorem is the following. So the theorem is that, let me see where. Okay, yeah, sorry. Yeah, sorry. So suddenly I thought this was the same file as this one, but they are not actually the same file. Okay, so the theorem is the following: take any Möbius transformation with exactly 2 fixed points. Okay, and then if nu is hyperbolic, then okay, if nu being hyperbolic means that it's conjugate to a homothety by a positive real number, right? Now, homothety by a positive real number preserves each common circle between 0 and infinity. Right? So this means that by very just by elementary conjugation, that each common circle of the 2 fixed points of my hyperbolic transformation is preserved by nu. Right? So if nu is hyperbolic, then nu preserves each common circle. Okay, now again, nu being hyperbolic, let's go to the homothety, and then each circle centered at infinity is mapped to another circle centered at infinity. Right? Well, centered at 0 as well. So this means that the family of Apollonius circles is permuted, right? And it's kind of is permuted in only one sense, right? So if in only one direction. If the homothety is by multiplication by alpha greater than 1, then everything gets away from 0 and it goes to infinity, and the other way around if alpha is less than 1. So in other words, the permutation is not just like arbitrary, right? But it's kind of well ordered in a way. Okay, so this is what I stated here, right? Each common circle is stable under the action of nu if nu is hyperbolic, and that nu permutes the family of Apollonius circles. Okay. Now, if nu is elliptic, then again, let's just conjugate and then see what happens in the case then of rotations. In the case of rotations, then each common circle goes to another common circle, right? Kind of also in order, right? I mean, the permutation is just not arbitrary. It's not like I don't know how the permutation looks like. I have a very good mental image of how the permutation looks like the permutation of the common circles between 0 and infinity, and each Apollonius circle of 0 and infinity is stable under the action of nu. Right? So what happens that if nu is elliptic, then each Apollonius circle is stable, and nu permutes the family of common circles. Right? So let's say in this picture, Mhm. Let's see. In this picture, if nu is hyperbolic, then we see each common circle is stable, right? So and then just like what happens with zero and infinity, that either everything gets away from zero or everything gets away from infinity and close to zero. What happens is that under my Möbius transformation, you see somehow the flow would somehow like look like this, right? So here each common circle would be stable, and these guys would be kind of mapped like this, right? So somehow with this direction that I chose for my picture, um, with this direction that I chose for my picture, um, somehow these Apollonius circles, they would be mapped to like bigger, etc., and then they would all approach like here, right? And then the flow would be along this. And when I say flow, what I really mean is that when you start iterating the positive powers of nu, you start moving away from one of the points and then close to the other point along each of these common circles, right? And look, it's not only that the common circles are stable, it's actually kind of each common circle is kind of split into two parts, each of which is stable, right? Like this part is stable, and this other part is stable, and here you have the fixed points. So okay, now in the case of the elliptic ones, what happens? What happens is this, that if we think of the origin infinity picture, where it's only it's simply rotation, let's say that the rotation is counterclockwise. Then let's say somehow the flow would be like this. So it really looks like as if things would be rotating around the fixed points, right? Now, in the case of zero and infinity, kind of one usually focuses only on zero, right? And then sees the rotation around zero. But around infinity, you also have rotation, right? So around infinity is kind of the other way around. So here, if you're conjugating Möbius transformation since zero to this point, and infinity to this point, then here it's how the rotation around this point looks like, around like zero looks like. But you see, you also have some rotation behavior around the other point, which somehow is the one that represents infinity somehow. And what happens is that it behaves well in this sense that when you have like this segment of common circle and you apply rotation, then it goes, you see, like this, and then it goes like this, right? So it's kind of, it starts getting rotated, but kind of but somehow like all together, right? So all together in this sense that like let's say like all of these intersection points, they all go to all of these intersection points, and then when you iterate again, then to all of these intersection points, etc. Right? Okay, and now finally, what happens if in the remaining case, right, which I have not analyzed yet, which is in the case where nu is loxodromic. In that case, neither of the two families is stable, and by this, and actually, what happens is that each family is permuted, right? And this is kind of, just think again about the picture 0, infinity, and you know, it's homothency followed by rotation. So it's clear that an Apollonius circle of 0, infinity goes to another Apollonius circle of 0, infinity, and that a common circle goes to another common circle, right? And well, that's what happens. That in that case, nu permutes both families. Some slightly more useful examples. I mean, more useful than just writing on the ones I wrote on the iPad. Right. So let me give some examples of Möbius transformations of with two fixed points. Let me start with a hyperbolic case, which is where, you know, it's conjugate to multiplication by a positive real number different from 1. So let me choose it somewhere around there, let's say. And let's choose the two fixed points, let's say here and here. And let's compute a matrix that gives me that Möbius transformation. Okay, so here let's say that I want 25 points in the orbit. So whatever number I put here, you see, let me put 0. What it's going to compute is going to compute 25 iterations of the Möbius transformation at 0. So it's going to compute nu of 0, nu square of 0, nu cube of 0, etc. Okay, so and that is how it looks like. So you see, since if you notice, this one was the point that I clicked on first, and this other was the point that I clicked on later. So the way it's programmed, the way I have programmed this, does it in such a way that then this represents 0 when I conjugate, and the other point represents infinity when I conjugate. And since my complex number was greater than 1, that means that when after conjugating, things get away from 0 and get closer to infinity. So this is why this one gets away from this point, which represents 0, and gets closer to the other fixed points, which represent infinity. Now let me move you see, if I move the point, then I can see more or less how the orbit, or the 25 first iterations look like, and then you see they all look like this really looks like they all belong to they all sit on a common circle, right? So I mean an invariant curve, right? I mean a stable curve, right? Being stable under the action, it means that it's a union of orbits. Right? Okay, and so let's see. If I click again, then it stays printed. Click again, it stays printed. And then let me do this a few times. I did it a few times. And so you see, I moved it a bit. I mean, and I didn't even do it so carefully. And you see here, so there's like a circle around here, right? But in any case, something you can see here is also the phenomenon of continuity, right? I mean, if I get this point close to this point, you can see how the image gets closer. The kind of each of these images get closer, right? So that's something else you can also see. And now let's draw some invariant curves. And then you see, and what you see there is just as the segment of the circle, of the segment of a common circle passing through the fixed points. That's what you're seeing there. Okay, now don't pay attention to this here. It says loxodromic. It should say hyperbolic, right here. But I imagine it's a floating point problem. Anyway, so let me animated orbit. So let's see how it looks like. I mean, when I animate, somehow things should get away from this and should get closer to this, right? Because they are iterations. Right? And then here you can see it. Okay. Now let's move on to giving an example of an elliptic transformation, right? So here I choose a number of on the circle. Let's say here, and let me choose the two fixed points. So the one that represents 0 and the one that represents infinity. So you see the fact that I'm choosing this point here, which is kind of counterclockwise, this automatically means that the transformation is going to look like here it goes like this, and around this one is going to do something like this. Okay, so compute matrix. All right, and then let's say again, let's start with 0. And then just a draggable orbit. Right? And then you see, I mean, just by looking at that, you see it looks like things that this orbit lies on some circle, right? Which now we know it's in an Apollonius circle. Right? Okay, so let's move around a bit. You see, and then you see how the orbit moves. Okay, and then around the other one, right? So what you are seeing there, I mean, the Apollonius circles around the 2 points are kind of, you already see them kind of sketched, right? Because, okay, I mean, better sketched if you just do this, right? So this is an Apollonius circle. And, yeah, okay. And this is how the orbits look like. Now let's see an animated orbit. So well, let me do one more here. So you see here, as I said, the fact that this one kind of it's slightly to the counterclockwise direction means that here I'm going to see something like this, and in this other I'm going to see something like this. So let's start. I hope you are able to see the red dot. Yeah. Right, and now let's move like here. Well, let's draw again the fixed points, draggable orbit, and then you see here. Now it's moving, but now it looks like clockwise direction around the other fixed point, right? Which is still counterclockwise with respect to the other fixed point. Okay. Clear, and then now let's have a look at a loxodromic one, right? So here I have this point that I put anywhere but the positive real axis and the circle. So let's say somewhere here, also close, you see close to 1. Close to 1, both in norm and close to the real axis, but not on it. Let's choose the two fixed points. This one that represents 0 and this one that represents infinity. And let's compute a matrix with that one. Pay no attention to this elliptic one. I hope to be able to fix this part of the program at some point. Okay, and then let's say again 0, and then let's start with something without the invariant curve, just 25 points on the orbit. And you see, it already looks like things sit in some sort of spiral, right? Okay, so where is the zero? This here is the zero. And let's move it a bit. Right, and actually, look, when I get closer here, right, so things seem to be on the spiral, right? I mean, there it's kind of clear, right? And then let's say now an invariant curve. Well, there you go. And this would be a loxodrome between the 2 points, between the 2 fixed points, right? Which how do I define? As I said in another video, I define it to be, just take the loxodrome, take a loxodromes for 0 and infinity, and then map them through a Möbius transformation, and that's what I call now a loxodrome with respect to a loxodrome for these 2 fixed points with respect to this alpha, right? This point, right? You remember that for 0 and infinity we said loxodromes with respect to the complex number by which you are multiplying. So in this case, it would be this complex number. I mean, the multiplier of the Möbius transformation, of the loxodromic Möbius transformation, right? So, okay, so when I move this one, and then here again, let's say again, kind of this to visualize a little bit of continuity of functions from the complex plane to the complex plane. Right. Okay. And now animated, right? I mean, as I said, somehow this one represented 0, this one represents infinity, this has norm greater than 1, so this means that somehow this must be the repeller and this would be the attractor. So let's see. All right, so I hope it's clear enough. There you go.